Morning, kiddies.
Morning, sir.
How you doing?
We are fine, thanks. How are you, sir?
I'm doing just fine. Today we'll be doing a practical experiment on a voltage divider bias circuit. We'll be using a BC547B transistor. I already checked the parameters. It can handle a maximum current, the maximum collector current. Let me just leave it like this, of 100 milliamps. The current gain they said is between 200 and 450. So now ours with the silicon. So the base emitter voltage about 0.7 volt. Now ours is to calculate the correct resistors to bias this transistor in active region. This is VCC. We'll be using 12 volt. This RC, RE1, R2. And this is ground. We know that to drive this transistor in active region, VCE is equal to half VCC most, and VCC is 12. So half of 12 is 6 volt. Beta, we have it. We just take 200. So now we need to calculate VE. They said VE is equal to 10% of the supply voltage, and that is equal to 1.2 volt. 10% of supply voltage is 12 is 1.2 volt. How to calculate that one? You say 10% over 100% multiplied by 12. The percent will cancel. 10 divided by 100 is equal to 0.1 multiplied by 12, and that will give us 1.2 volt. Did you get that? So now we have VCE. We have VCE, which is equal to 6 volt. VE, not VE, is equal to 1.2 volt. VE is equal to VB minus 0.7 volt. We already have VE, which is 1.2, is equal to VB, and that's what we're looking for, minus 0.7 volt. If we transpose 0.7, it becomes positive, and then you add it to 1.2, then it gives us 1.9. 1 plus 0 is 1. 2 plus 0.7 is 9. So VB is equal to 1.9 volt. We are moving. We can calculate IB if we need it. We will use beta, but let's leave IB for now. IC, we want to limit this to 2 milliamps like previous. So we keep it that way. Now we need to calculate the resistance. Since IB is too little, normally is in micro amps, so we usually say IE is approximately equal to IC, so IE is equal to 2 milliamps as well, They're not exactly equal, but they're approximately. So to calculate the value of RE, which is this resistor, we'll say VE divided by IE. VE is 1.2 volt, IE is 2, then RE is equal to 600 ohm. We don't have a 600 ohm resistor, so the closest one we can take is 560 ohm. So if RE is equal to 560 ohms, Now with this we can calculate RC. VCE is equal to VCC minus IC into RC plus RE. VCE is 6 volt, VCC 12. IC is 2 times 10 milliamps. RC is what we're looking for. RE is 560. 6 minus 12 is minus 6, we divide by this on both sides. Divided by minus 2 is equal to RC plus 560. We can say therefore RC is equal to this minus 6 divided minus 2 milliamps gave us 3000, then 3000 minus 560 gave us 2440, which is equivalent to the result that you can get in this range is 2.2 kilo ohm. So RC is equal to 2.2 kilo ohm. Now we want to calculate the network resistors, the voltage divider. R2 over R1 plus R2 multiplied by VCC. We just take R1 as 100 kilo ohm, we get this value. And then VB, we know VB is 1.9 volt, is equal to R2 that you are looking for, all over 100,000 plus R2. We multiply everything by 12. Now we work. We can divide both sides by 12, that gave us 0.16 is equal to R2 over 100,000 plus R2. We multiply both sides. Can take this one this side, 16 down. R2 is equal to 7 ohms. The resistor that is approximately equal to this one is 18 kilo ohm. So we have that R2 is equal to 18 kilo ohm. Now we have all the values that we need. Now we can build the circuit. The capacitor values, I will touch the capacitor calculations when we start to do the RC circuit. But it's equal to XC is equal to 1 over 2 pi FC. We'll get to this formula someday, ne?
Yes, sir.
That's the formula used to determine this capacitor. Now let's go to the workbench. Okay, kids, this is a BJT transistor, ne? This one specifically is a BC547B, ne? It's an NPN transistor. So now, when it is like this, how do you know which one is the emitter, which one is the collector, and which one is the base? You don't know, ne? It's either you search on the internet or you measure it yourself. So to check which one is base, emitter, and collector, you must first turn your multimeter to a transistor, ne? To the symbol of a transistor. It's an NPN, ne? So the middle one is N, of course. The other one is P, NPN. Yeah, that's true. That first outer leg give me 691. You must keep that number in mind, ne? Then I move the probe to the next one. This one give me 698, which means the middle one is the base, and the first one that gave me 691 is a collector, and the other one is an emitter. But why? The emitter will always give you a bigger number, ne? Remember that the emitter is heavily doped, ne? They have a lot of charge carriers. So when you measure it using a multimeter, it will give you a greater number than the collector, ne? Always. If it's an NPN, the positive probe goes to the middle, the other probe goes to the other side, ne? You check the first side, you write down the number, or you keep it in your head, and you measure another leg. The one with the greater number is an emitter, ne? Now let's put the resistor values. We said RC is 2.2 K, ne? You can check there on the board. RC is 2.2 kilo ohm, and 2.2 is a red, ne? We said this one is a collector. So this one is our RC, and our RE goes from the emitter to ground. What is the value for RE? 560 ohm, ne? What is our R1? R1 go from the base
100 kilo ohm.
100 kilo ohm, ne? And it go from the base to VCC, ne? From the base to VCC. What is our R2?
18 kilo ohm.
18 kilo ohm. Yes. From the base to ground, ne? That's how our circuit will look like. This is ground, is black, and this is VCC. Make them red. Then before we inject the signal, let's first measure our voltages, ne, to various points. We said what is VC or VCE? What is VCE?
6 volts.
Say the 6 volt, ne? Let's see what is VCE. Here we get 6.68. We are off by 0.68, ne? We are not that far off. So our transistor is operating somewhere in the active region, ne? We said what is our VE?
1.2 volt.
1.2 volt. VE. We get 1.0, let's say 7, fluctuating between 6 and 7. You see, you are off by 0.05. Not that bad. What's another voltage that you need to measure? Which one? We can just measure VC for interest's sake. What is our VC? 7.72 volt. Yeah, let's check if it will operate, if this circuit or this transistor will operate in the active region. Everything looks good so far. I'll be using 47 microfarad as my capacitors. Why do we add these capacitors in between, or between the input and the output? To eliminate the DC voltage. Remember that capacitor blocks DC and allows AC. Our input goes to the base through the capacitor. Now, can you see that our transistor is operating in the active region?
Yes, sir.
But we are close to saturation. Let me see. Let me just reduce that. Yeah, can you see that now we biased our transistor successfully in the active region? Our input frequency is 10 Hertz, but yet it gives us 13, but fluctuate. This is our input signal. Our input is 111 volt, and our output is 3.95 volt, and it stayed right there, 3.95 volt. This is the input signal. This is the output. The input means if you put this signal into this circuit, this is what you get outside. If you were to sing, maybe this will be your voice. You see how small your voice is. When it comes out, it will be louder. Can you see that?
Yes, sir.
That's how you bias a transistor to amplify a signal. Can you see that? And then if you increase the input waveform, you will see it will clip, because now we drive it to either saturation or cutoff. Let's drive it. Let me show you. You see it clips. You see it clips. Even here it gets distorted now. Because now this amplifier or this voltage divider bias that we just did, it cannot go beyond 12 volt peak to peak. If it try to amplify the signal above 12 volt peak to peak, it just clips it. If I take it back to see the gain, 1.2. Where's the calculator? Let's say 1.15. Let's just freeze it and stop. If you freeze it, you see that the input voltage is 1.13. So to calculate the gain is by how much we increase the input signal. To calculate the gain, we say 4.12 divided by 1.13, and the gain is 3.6. So for whatever input that you put here, you will multiply the signal by 3.6. That's how much you're gonna get out of the signal. Yeah.
Yes, sir.
Next time we'll build an audio amplifier, and then someone going to sing to hear your voice getting amplified. Ne? So now did you see now how the voltage divider bias work now?
Yes, sir.
Yes, we biased it, we calculated the values first, then we biased it, and then we saw it amplifying the signal without clamping it in the beginning. Ne? So actually what's happening more or less is like VCE that we set it most at half, ne? And this one will be VCC, and this one will be 0 volt, which is ground. This one is half of VCC. Today we had 12 volt. That's 12 volt, and VCE we made him 6, ne? So this 12 will disturb us. Just leave him, ne? So basically the signal that we put in here in this capacitor to the base goes something like this, ne? It only fluctuates within this range, ne? You saw that?
Yes, sir.
So as I increase the amplitude is from here to there, ne? This is the amplitude of this circuit. As I increase the amplitude, you saw that here it started clipping, ne? Started going something like this. As I increase the amplitude, it says, even here, it says that I cannot go beyond these parameters, ne? Something like this. That is why you set VCE to half of VCC, ne? So that the signal can be in the middle, and then it can swing nice between ground and VCC. So the same thing happens if you don't bias this signal. If you don't bias this transistor, the signal might swing. Sometimes it doesn't just get big, ne? Because the transistor is unstable, since it is not properly biased. Sometimes the signal, instead of staying in the middle like this, it just do something like this. It do something like this, ne? Then it gets here, it cuts, and then it swings nice. Get here, it cuts, and then it swings nice. That's why it is important to bias a transistor before you use it to amplify the signal, ne? We bias it to the active region, ne? And then to calculate the gain, you can also calculate the gain using the resistors, ne? This is the symbol for the gain, ne? Voltage gain is equal to minus RC over RE, which is equal to minus. This minus indicates that the signal will be 180 degrees out of phase, ne? Which means it will be the opposite of the input signal. What is our RC? RC is 2.2 K divided by our RE is 560. And we get, let's say the absolute value, 3.9. You see, we are not far off from the gain we were getting in the oscilloscope, ne? This is the gain. Meaning, if you put, I'll rub this off again. Meaning, if you put the signal, let's say that one peak to peak, it was 1.04 volt, ne? 1.04 volt multiplied by, but we got an oscilloscope 3.6, going to be 3.74 volt. So any value of a signal that you put here will be multiplied by this number in the output. This This is the gain we got on the oscilloscope, which is approximately equal to the one we calculated using RC and RE.